All right. So good morning and good afternoon. Thank you for joining the Lattice Developers Conference. So in this breakout session, you will hear about the first small FPGA with hardened USB interface and the tools to develop useful USB applications. My name is Peiju Chang. I'm Product Marketing Manager at Lattice Semiconductor. I manage the video connectivity FPGAs as well as the control and security products. The Lattice video connectivity FPGAs feature the Mobile Industry Processor Interface, also known as MIPI. So this standard interface is commonly found in many image sensors. So I have worked with many developers to enable image sensor connectivity solutions. Today, we will focus on the image sensor bridging over the USB interface from a low-power Lattice FPGA. Joining me today is our partner, TinyVision.ai, Venkat Rangan, founder and president of TinyVision AI, will showcase their innovation in hardware and FPGA development tools in the second half of this presentation. Hi, Venkat. Please introduce yourself.
Thank you, PJ. Yes, it's a pleasure to be here in this breakout session. A little bit about my background that may not be covered in the slide here is I like building stuff. I'm a maker at heart, and I've been building hardware since being a little kid. So it's great to play with these FPGAs where you can change things on the fly and get that nice hit of making your design work. I was at Qualcomm for a very long time, left about 5 years ago and founded TinyVision.ai. We'll talk a little bit more about the background. To summarize, we're a small business and provide a variety of design services focused on enabling edge AI devices. So over to you, PJ.
Yeah, thank you, Venkat. So before I go over the agenda, I really want to quickly talk about the adoption of USB in FPGA. We generally find USB 2 controllers in the FPGA SoCs. These are part of the SoC feature, right? They have the USB 2 controllers actually requiring a USB low pin interface called ULPI. These are basically an 8-bit parallel bus so that you can connect the FPGA with an external USB 2.0 PHY chip. So it is a two-chip solution. For some of them, where they want to use the USB 3.2 speed at 5 gigabits per second, they have to use a generic SerDes and all the resource within an FPGA to implement the full USB controller and PHY stack. But they will also need the external USB 2.0 PHY chip to fully comply with USB standard. So none of the above approach is straightforward. So here at Lattice Semiconductor, we offer a more integrated and easier to use FPGA solution for USB applications. There are many opportunities in USB today, especially within the camera sensor connectivity. So with today's agenda, we'll begin by looking at the role of USB in camera sensor module connectivity, how Lattice will address the need with the latest Crosslink UNX FPGA, and then I will hand off to Venkat to talk about TinyVision's system on module approach that can accelerate development around the Crosslink UNX FPGA. We will end the session with Q&A. You can submit your questions through the Q&A widget, and we will try our best to address them before the end of the presentation. Okay, so with that, let's talk about the USB camera market. So based on the data collected from various industry reports, the industrial and automation camera market will double from 2023 to 2030. This is really driven by the increased adoption of edge AI in factories and in manufacturing facilities. We need a solution that can be easily deployed in different manufacturing settings. Only a portion of these smart cameras will use the USB interface, but it will be a significant percentage because the USB is really simple to deploy. There is a large ecosystem of PCs with USB 3.2 host capability in the industrial settings, and USB camera sensors can use the processing power in the industrial PCs to enable edge AI. So with all these advantages, with USB is being adopted in this growing industrial camera deployment. So let's look at how the camera sensors connect to the processors today. Most processors don't offer the exact signal interfaces from industrial image sensors. FPGAs have always been the bridging device to move image sensor data to the processor. The FPGAs can also apply simple ISP or image signal processing to the image sensor data or process via edge AI algorithms. So in this diagram, you are seeing the lattice crosslink NX FPGA devices have the ability to bridge MIPI CSI2, sub-LVDS, and parallel sensor interface to the different interfaces on the processor, right? Those include also MIPI CSI2, PCI Express, Gigabit Ethernet, and USB 3.2 interfaces. And this really provides a wide range of options for deployment in the different industrial settings. In the next slide, I want to take you through some of the characteristics and how these deployments typically happen. So if we look at the camera module interfaces matching with the of what's available on the processor, on the very top, you see the USB 3.2 up to 5 gigabits per second, plenty of bandwidth. It's somewhat limited by the length of the cable, so it's typically a shorter range of application, around 1 meters. It has very low latency, and the most appealing part about the USB is the ability to do plug and play. So you can very easily accessorize, make it as an add-on, and then when you think about deployment in these type of dynamic industrial settings, it is very useful that to build an accessory around it so that you don't have to consider too much about full system integration. If we look at the Gigabit Ethernet interface, it has a range of bandwidth, 1 gigabit to 10 gigabits per second. That's really great. These networking type of sensors has a long range, up to 100 meters. Due to the fact that it has to deal with different network protocols, it suffers in latency. It's not plug and play. It has really to fit into the overall network system. You have to configure it, right? So from a design fit standpoint, it's very much used in a multi-camera deployment scenario. If we can group the next two together, if we look at PCI Express, MIPI DeFi, these interfaces have good bandwidth, as we can tell from here. The range, however, is fairly limited because these are typically limited to board-and-board connectivity. It has very low latency. It is not plug and play. So for using these type of interfaces in the design, really rely on thorough system integration and design consideration. So comparing all these options, USB camera module are really easy and simple to deploy while offering good performance. And so this is why we think it's a great combination. You get the best of both worlds with combining USB and low power FPGA. With USB, you have the most successful interface in PC history. Plenty of processors out there has the USB host interface. This is flexible. You can do plug and play, and we can easily accessorize and design products around this huge ecosystem. And it is also a very popular interface for industrial sensor modules. Looking at low power FPGA, it's getting very, very important that we need to reduce the form factor on some of our designs, especially within camera modules. We're seeing multi-camera type of deployment, so reducing the size is very important. And that's where low power come in. It allows very compact form factor. And the fact that you have FPGAs, you get all the resources you need, so you can customize different ISP functions as well as edge AI capabilities with the FPGA from Lattice and create differentiating features for your use case. And that really allow you to stand out from your competition. Okay, so let's look at the different features offered by the Crosslink U-NX FPGA. We really want to highlight the hardened USB interface. This includes both controller and PHY. We support USB 2.0 up to 480 megabits per second, as well as USB 3.2 Gen 1, 5 gigabits per second. Truly integrated solution. And on the right-hand side, with regard to improving low power, we have this always-on block. It is a dedicated block that enables low power standby less than 70 microamps in a typical use case. Coupled with the fact that the FPGA can quickly configure itself within less than 15 milliseconds, you can see the FPGA can operate in a operating mode and also within standby. As you quickly switch between those two in a certain duty cycle, you effectively reduce the average operating power consumption of your system. The FPGA fabric is optimized for AI. You get 33K logic cells density. You have 64 DSPs for computation, and we offer up to 3.7 megabits of embedded memory. This is where you can store the different weights that you need for the different AI algorithms as well as networks for machine learning. And on the right-hand side, you immediately see that we treat security very seriously. We want to protect the IP and the designs that you build. So we offer bitstream encryption with AES 256, as well as authentication using ECC 256. Also, some of the security blocks is open for user to access. You have true random number generators, AES blocks, as well as hashing functions such as SHA. So you can use those on the user data within your design. Also, the best part of the FPGA is you get this versatility in the programmable IOs. This allows us to interface with the popular sensor interfaces commonly found in the industrial and consumer settings. We're also able to interface with processors, so you can open a communication channel between the processor and the FPGA. From an availability standpoint, we offer two packages. The 84-ball wafer level chip scale is very small form factor for very small designs. We also offer the 104-ball flip chip CSP, and those are more applicable in industrial settings, but both are great choices for your design. From a software support standpoint, we have the Lattice Radiant 2023.2 as well as the Propel, both supporting this device. In the next two slides, I will talk about the benefit of having the hardened USB interface and the always-on block. So Lattice Crosslink U-NX FPGA is the first vision processing FPGA with hardened USB 3.2 interface. In the past, developers must build a USB sensor module using multiple chips for bridging. So you got one FPGA to interface with the image sensor, and then a USB bridge chip to interface with the FPGA over typically a 16-bit or 32-bit parallel interface. Then you got the USB 3.2 interface to the processor. Integrating the FPGA and the USB bridge into a single chip reduce the design footprint and the total cost of ownership. And this is the opportunity that Lattice really see by introducing the Crosslink U-NX FPGA. From a low power, we know that it is essential for all system designs. It reduced the extra cost associated with thermal management, enabling smaller form factor. It extends battery life, and it is also good for the environment. So the always-on feature in the Crossing UNX is a dedicated block that manages the FPGA entry and exit from the standby state. We have a programmable standby period setting where it's configurable between 1 millisecond all the way up to 64 seconds. So by controlling that, working with the instant-on capability of the FPGA, you can create a wake state as well as a standby state as presented in this diagram here. So as an example, we observe up to 6 times power reduction in a typical application. With the wake period using 180 milliwatts, standby can go all the way below 126 microwatts with an average power consumption of 30 milliwatts. So it's with these 2 new features, as well as all the features in the Nexus device, that we can enable a broad range of applications, such as factory automation. We talk about industrial camera sensors. In medical imaging, some of these probes, you can build an accessory that can plug into the different medical instruments that has USB interface. Consumer and PC cameras are a big space where you have a huge install base of the USB host devices. A lot of innovation can happen there. With test and measurement instrumentation, these devices also have USB interface, so you can build the different probes and test modules for these type of use cases. So overall, the Lattice Crosslink NX FPGA family now offers a comprehensive connectivity and processing solution between sensors and processors. If you take a look at this table here, the different families of Crosslink NX devices, the 17K and the 40K devices have been in production for the past 2 years. They offer PCI Express, Gigabit Ethernet, as well as MIPI D-PHY. With the addition of Crosslink UNX, we really expand that capability to USB 3.2 and will enable a lot of new applications. So to facilitate this early USB design and prototyping, Crosslink UNX has its own evaluation board like all other Lattice FPGAs. The board comes with a connector for the Raspberry Pi camera module. So you can order these cameras online. It'll work with many different variations. It's got a great ecosystem of these camera modules. We offer 2 PMOC connectors for you to do any type of sensor and I/O bridging functionality. We have this USB 3.2 receptacle. So it is a connection with your PC for development. We got a 128 megabit QSPI flash, enabling instant-on FPGA boot up and configuration. And also an onboard 256 megabit PS RAM for frame buffering or temporary storage of the sensor data. This is designed to enable MIPI CSI2 image sensor bridging as well as processing applications. You can find all the information. I want to give you all the links so you can take a look at all these resources on the Lattice website. You want to go to the Crosslink NX product page that contains everything. You got an example on the right-hand side. And you also want to check out the design software to enable your development. The Lattice Radiant offers RTL design, simulation, as well as place and route. You got the Lattice Propel, enabling RISC-V processor design environment. I also encourage you to learn about the USB IP. While the FPGA USB block is hardened inside the FPGA, we do create a wrapper IP. So you have known and easy to use APIs to communicate with a hard USB block. And then lastly, try out our reference designs. This offers a quick prototyping code so you can see how you can interface USB to different type of GPIOs. So as a very good example, we engaged with our partner, tinyvision.ai. So this is where Venkat can take you through some of the things that he's doing to enable new applications on this new FPGA. Venkat, go ahead.
Thank you, PJ. Yeah, the Crosslink U NX is a really interesting FPGA, and so want to just bring a little bit of background about the company. So TinyVision, like I mentioned, we are a very hands-on company, and our primary goal is to really help customers build real-world products. And like I like to say, from paper napkin through production. And our strengths are in the deep system knowledge that we bring to the table that is really required to take an idea and build product out of it. So we have access to local surface mount machines that help us to build hardware very quickly instead of outsourcing that. And the significant advantage of that is the hardware we produce is really DFM friendly. So it's designed for manufacturing. It's not a prototype that you can't take it to production, right? We've been in business for 5 years, and we're quite active in the TinyML community. That's our way of giving back. I host the TinyML Builds series where we talk to various companies about how products are built. Offer internships to students, high school students as well as college students, and we mentor and sponsor our local robotics team called Team Inspiration. They're really amazing bunch of high school and college kids. On the next slide, yeah, a little bit more detail of what we do. Our process is really, we work closely with the company that we are engaging with, figuring out with design and consulting services, defining a product and the functionality, what should it do, as well as the system architecture. Where is the hardware, where is the hardware firmware trade-off, which is really important, what kind of sensors to use, what kind of software do we need in the system. And once that's done, we help them to build hardware. We do all the way from schematic layout, board fabrication. We have in-house development of FPGA RTL and embedded firmware. So once that's done, we work with the companies to really help integrate this into their systems. Now, as many of you are aware, a lot of devices now have Edge AI built into them, and PJ mentioned that this is one of the significant advantages of this FPGA. It's really built for AI. So there are large amounts of memory and a lot of DSP elements that help with this. We work with our customers on the AI side of things to help them define the model architecture that is required, help them with data gathering and curation that is really important and often not really appreciated in how complex that is, all the way through training models and deploying it on the FPGA. To give you an example, we've deployed an audio keyword spotting model on the really small Lattice ICE40 Ultra Plus 5K, which is just 5K lookup tables. So we should have a demo at our booth. Do come by and check it out. 33K lookup tables is significantly more, so we can do a lot more with that. Some of our products that are on our website are really used by makers in many universities around the world. for undergraduate courses and senior projects. Encourage you to check it out at tinyvision.ai. So on the next slide, want to really dig into the details of what we're talking about, right? Which is, there's a large number of smart camera use cases. Now, what differentiated this smart camera from a regular camera? A normal camera system, its function is to convert light to video streams, right? And then the video stream is sent over one of these different interfaces that PJ mentioned to a host. Their processing is done and action is taken. For example, you might want to classify a package as going to Oklahoma or going to California, whatever it is. Or you want to check for whether there's a barcode, is the bottle full, for example. There's so many industrial use cases, right? And that is the current architecture in most industrial systems. A smart camera is a little bit different. It can not only provide a video feed, but do some sort of image processing right in the camera itself. This may be as simple as doing auto exposure and auto gain and a few image manipulations like image smoothing, all the way through object detection and classification. For example, a smart camera might be able to say, hey, this is a box with so-and-so dimensions. Or it might be able to say, here is the barcode that I read on the box. And all that's done is you send just the data. You do not send the entire image. There's no necessity to send the image. By moving the processing to the camera, you can see a significant gain in latency and savings in bandwidth and storage. Now, you might wonder, why is latency important? If you have a long conveyor belt and you have to take a camera that takes images and there are buffers involved, send it to the host, and then the host decides what to do. If at every stage, when you switch protocol, especially, there are large amounts of buffers. So it takes multiple frames before the host can even get the data to process it. And an FPGA-based approach, on the other hand, within a single frame, can do the processing right on the camera and send the data back. Now, this can result in savings, actual physical savings. For example, the conveyor belt doesn't have to be as long to make up for that delay. Right? So this is where the world is going by pushing more intelligence to the edge. The Crosslink U is a significant adder to this ecosystem because of the USB interface that it provides. So we have a quick demo for you. And before we get into the demo on the next slide, just want to give you background on it. Do come by the booth and check out our full demo. The demo that we have recorded for you is we have a system on module. We've taken really the developer kit that PJ talked about and compressed it into the size of a 1 inch by 1 inch system on module. This is running Zephyr as an operating system, and it is enumerating over USB 2 at the moment onto a laptop. So let's go ahead and take a look at the video. So we first took the lattice reference design that PJ mentioned, and the SOM will enumerate. Here you see a debug serial port that is going to, as soon as it's plugged in, waits for the USB. Once the USB is plugged in, it enumerates right away. And you can see that it shows the lattice width. We took the same core and wrapped Zephyr around it. And that is really important. We'll talk about it more. Here you see a simple serial port that's printing hello world. On the next slide, want to cover why we decided to build a system on module. So in industry, this is a pretty common approach. You'll find system on modules for all kinds of processes that are relatively complex, right? So the function of a system on module is to take a chipset and abstract it and provide a very fixed set of electrical, software, and mechanical interfaces. Now, the significant advantage here is that you can take a SOM, assume that it has already been productized and it's production ready. So you get a very fast time to market, right? And it's excellent for all the way from prototyping through medium volume. Let's say there's a new device that comes up in the future, you just swap out your SOM. If you have an RMA, if you suspect the SOM is bad, you swap it out, right? So it makes it very easy to pull things off. It's a very modular system. Another significant advantage is that this enables a whole ecosystem of developers. Developers can now assume that there is a fixed set of interfaces. For example, in the FPGA, there'll be, what is your pin constraints? Right? There's a lot of confusion of getting it right, just right. All that is provided to you. There is a framework that is typically provided by the SOM vendor, in this case us, and we'll go over some of the details. Now, SOMs are not necessarily the best for everybody, right? Because it's a one-size-fits-all. That doesn't work. So especially for very, very space-constrained applications, there are the CSP package that PJ talked about, for example, we do not use that. So if you have a very space-constrained application, a SOM is probably not the best thing. It makes sense to take the design, license it out, and then build your own version of it. And of course, when you go to high volume, there is overhead. There are connectors, multiple connectors involved, for example, and multiple boards. All of that is scope for optimization, for cost optimization when you go to high volume. So just on the next slide, really digging into the detail of what I covered is SOMs offer a huge time to market advantage. You can take effectively what is a developer kit that we provide and assume that you can have the same thing in production. You can build prototypes very quickly because you can take the SOM and populate it on a very, very low complexity board. You don't have to worry about breaking out a VGA and expensive board layout. So it extends all the way from system design through integration and test. All of that gets compressed. And so you can really focus on the deployment aspect and the design aspect instead of worrying about, does this thing work? How do I debug it? Right? The next slide goes over the details of what we have. So we have, of course, the featured Crosslink UNX FPGA. We ported a soft-core RISC-V processor onto it, and we support exactly the same amount of flash and the SRAM that is on the dev kit. In fact, even the connectivity, even the pinouts on the SRAM are exactly the same. Right? So we've taken that and squished it into a really small form factor for you. As for the interfaces on the right, we handle exactly the same interfaces. There's USB 2, USB 3.2 Gen 1. We have two flavors of the module. Now, it's not really one size fits all. It's two sizes fits all. So we came to the realization that customers, not all of them need an SRAM. And if you don't need an SRAM, you can use those I/O for your own purposes. And so we have two flavors. One is called the connectivity flavor, which does not have the SRAM, and we bring out those. So you can handle up to 7. So we provide you 14 differential pairs. You can use them as differential pairs or just I/O on that flavor. The one with the SRAM, we call it the compute module, and that offers 6 differential pairs. The power interface is really simple. It's a single 5 volt. That's what you expect in a USB device, right? So you apply 5 volt, it works. It's onboard clocks. In terms of the frameworks, we'll get into a little bit more detail. We support the industry standard Zephyr RTOS that runs on the RISC-V. The demo that you saw earlier of USB enumeration with the CDC, that is running Zephyr RTOS on the 33 device. Of course, it's a lattice part. We support the Radiant and Sense AI frameworks. So if you want to do your AI applications, we have that. We will talk a little bit more about StreamLogic in the next slide. And we also took the open source, sorry, if you could go back. Litex is also another way to integrate RTL. Just a little bit more on the production side of it. This is a fully verified design. It is very small, just 3 grams in weight. That is very important for applications such as drones. We have a couple of reference designs available, and there has been a lot of sensitivity to where devices are made. These are manufactured in the US, if that is a concern for you. So on the next slide, the frameworks that we enable we lean heavily on Litex, which is used for generating the RTL, and the Zephyr operating system. Now, it's easy to go and say, hey, you know what, we have a RISC-V processor. What do you do with it? Usually, coding bare metal is not scalable. So we worked hard to get the USB core integrated into Zephyr. And so you can have a good development environment, a stable one that is known to be industry friendly. We provide you the framework. In that, there's a single script. You just run the script and it installs the whole tool chain for you. You don't have to worry about, is this Python version compatible or not? I mean, that can be a whole project in itself, right? So we try to make it easy for you. On the next slide is a little bit more about detail about StreamLogic, which I mentioned. So the challenge for developers is, hey, can I find an FPGA developer who knows about this part and also is capable of handling image processing or neural networks? How do we do all that, right? There are far fewer FPGA and RTL coders than C coders. So it becomes a bottleneck usually. StreamLogic is a tool that one of our partner companies has developed, which is a no-code graphical drag and drop FPGA design tool. And it is really, you draw the data flow and the RISC-V gets access to the control. Press a button and out comes a bit file. And this is using pre-verified IP that is part of the tool. You can see some of the IP on the right side, so you can do all the way from simple things such as downscaling all the way to creating your own neural network. And this was what was used in some of the in the keyword spotting demo that we have for the I-40 that I mentioned. So let's look into an in a potential use case on the next slide. Let's say we have a drone that we would like to have onboard processing and also have an FPV view of it. Right? So the drone camera connects over MIPI to the SOM, and on the SOM you see above the SOM the actual what the StreamLogic tool enables you is you take the camera feed, convert it to grayscale, and send it to the neural network. And you can also send it over USB 3 to a radio so that the FPV can be seen. The onboard neural network can be used to determine things like figuring out the right place to land, for example. So on the next slide, we are planning to, this is our design roadmap for people who are interested in using our tools. We have the compute module today. That is what the demo is running on. Next, we have the tiny camera reference design that really brings the capability into a small form factor that you can pretty much use as a real product even. Connectivity module will come later, and that's the one with more LVDS pairs instead of the SRAM. In terms of applications, we're focusing really on getting a reliable data pipe through. It is not trivial to handle the 5 gigabits per second throughput on the wire. So we are working hard to enable that. Once that has been tested and working, we have UVC so that you can plug it in and it will look like a webcam. That is a significant advantage. The industry uses USB 3 Vision and GigiVision. Those will come soon after that. In terms of looking ahead, we will have the compute flavor SOM developer kit and the tiny camera available at the beginning of the year. We have prototypes already functional today. In terms of how we like to engage with our customers, we have a reference design for higher volumes in addition to the SOM itself. And if you would like to customize the SOM or have RTL and firmware for specific applications, we're open for design services. Check us out at tinyvision.ai and email us if you can. If you're interested, please stop by. Thank you very much. Over to you, PJ.
Yeah, thank you, Venkat. Yeah, thank you for showing all the nice things that you have done. Look forward to the new applications you can enable with the new module and the design. So with that, let's go into the Q&A. Let's see what we have in our widget right now. Okay, let's see. All right, first question. So does Lattice offer ISP and Edge AI solutions? So yes, we do. And a lot of those are actually documented on the Lattice website. We do offer IP cores as well as what we call solution stack. Actually, the Edge AI solutions is what we call the Sense AI solution stack. So you can go check out the Lattice website. There's a lot of information around it. And in fact, since this is the first day of the developers conference, there are 2 more days of events that you can sign up, and there are topics around these type of use cases. So I would encourage you to also take a look at those breakout sessions. Okay, second question I see. Okay, so when and where is the Tiny Vision's SOM available?
Yeah, the SOM, like I mentioned, should be available in January. It will be available on our website, so feel free to go check it out. We will make an announcement on the website as soon as it is production ready. We will have developer kits, the camera reference design, and the SOMs available.
All right. So the next question is also to you, Venkat. So what kind of cameras can be connected to the SOM, and how many?
We are limited. I would say that pretty much any camera that is following the MIPI standard. MIPI usually is either 1, 2, or 4 lanes. We can handle we have a total of either 6 uncommitted lanes or 14 lanes, depending on the flavor of the module. So each, if you wanted to maximize the number of cameras, you can connect 3 one-lane MIPI cameras to the compute module, or you could connect up to 7 single-lane MIPI cameras. Now, if you have 2-lane and 4-lane MIPI cameras, of course, that changes the numbers.
Okay. Yeah. So it depends on really the video bandwidth you need relative to how many lanes available, right?
Yes, and also some sensors are temperamental. They don't want to support 1 lane, so they want to support 4 lanes. So you'll have to look at the sensor specifically. The Raspberry Pi camera, for example, that we are using wants to support 2 lanes or 4 lanes. They do not want to go to 1 lane.
Mm-hmm. Great. Okay. Okay, right. So the next question. So when can I order the Crosslink UNX FPGA and the evaluation board? We announced the device back in September. So the product is going to production in the Q1 2024 timeframe. So you also see the evaluation board associated with it around time. I would say more around the February timeframe in 2024. Okay. So, all right. So a lot of questions for you, Venkat. What's the RTOS does it support?
So the FPGA has a softcore RISC-V, so we can instantiate that. Now, exactly what runs on it is really up to the customer. Free RTOS is something that I think is very accepted. It's a very compact footprint. Zephyr is something that we see coming up and is widely accepted in the industry. So we have really settled on Zephyr. The USB is the really sticking factor. You have to have the OS connected to the USB core with a driver. So the driver is not a trivial thing. So we put in a lot of effort into writing the Zephyr USB driver for this particular FPGA.
Yeah. Okay. Then next question is, what AI use cases can I run on this solution?
So if you look at the Lattice website, I'm assuming that's for me. Peter, would you?
Yeah. That's more specific for you, but yeah, I can also address that a little bit, right? So, yeah. So like I mentioned before, there was a formal question about the edge AI solutions, right? The Sense AI does cover lots of AI use cases, right? Object classification. It really depends on what type of edge AI you want to use. So the Sense AI stack really offers a list of those functionalities. I think they probably interested in what kind of plan does Tiny Vision have, or what have you enabled in the past?
So from our point of view, we provide you the infrastructure to get started, right? And after that, you can take any of the Lattice reference designs and put it on here and have it work. In addition, we provide you with the capability to do audio processing as well. That is coming up. So far, in this talk, we've really focused on vision, but that's not what these FPGAs are limited to. So you can do a variety of sensor processing. So those are all things that we can help customers enable.
Okay. Yeah. So the next question really relates to what you just addressed, right? So you can also do something that's non-image related. So the exact question is, can I use this for non-image data as well? You mentioned audio. What's the plan?
Absolutely. If you remember, we went through our the roadmap. The first thing in the roadmap is a data pipe.
Yeah.
At the end of the day, that's really what these FPGAs are good at. This is really a USB data pipe. Now, what you run over it is you can run camera data in various formats that we talked about. At the same time, those are coming from the sensor to the host. There's nothing that stops you from driving backward as well. So for example, you can use it for as part of a logic analyzer, where you are capturing just signal data. You can use it as part of a software-defined radio where you might be receiving and transmitting. You need reasonably high bandwidths if you want to push most of the radio into software and just have the symbols be sent over the wire. So there's a variety of applications, really, a lot of industrial use cases where there is no camera involved even.
That's good answer. Yeah. So the next one is people are interested in how quickly does the does the module actually, sorry, the FPGA wakes up from sleep mode? Since we mentioned this, switch between operation and wake and standby, right? So in the presentation, I did point out that the FPGA reconfigures and boot up in less than 15 milliseconds. So that's the length of time it takes for the FPGA to reload its logic. So this is around less than 15 milliseconds. That's your answer. Okay, and all right, the next two. So the next two is kind of related. I'll just ask in one shot. How do I attach a display to the song? And how do I add new sensors to the song?
So the way that I think about it is the great advantage of an FPGA is that the I/O can be set within a bank to whatever standards you want. Right? So if you want to talk to a display, then there's a standard called the DSI. So we can support display using that. If you want to connect to a sensor that is at 1.8 volts or even 1.2 volts, for example, or 3.3 volts, we have a bank of I/O with programmable voltage that can be used to connect to that. So you can run SPI or I2C, for example, any custom protocols. All of that is certainly possible simply by writing the right RTL. And of course, there's a processor available that you can use.
Okay. Next one is, okay, can I connect to the SOM, right, through a network? For example, a wireless network, Ethernet network. How do you get access to the SOM module?
Very similar answer, really. The FPGA has, think about it as a processor running Zephyr, right? And you can write a driver to connect it to wireless, say like any of these little wireless modules that are available over SPI, or you can connect to Bluetooth over a UART. Those are for pretty low bandwidth data. You can also enable gigabit Ethernet, for example, using the RGMI, which the FPGA supports.
Yeah, by the way, do you know whether Zephyr supports the network stack? Ethernet?
Yes, it does. Yes.
Oh, it does. Okay.
Yeah. Yeah.
So that's good. There you have it. It's part of the OS, so it'd be very easy to integrate. So okay, the next question is, okay, can crossing UNX FPGA support the USB Type-C connector? So absolutely. While we show there in the picture uses a Type B, but this supports the USB 3.2. So it's just a matter of system design around it. You need a way to detect the cable orientation. So that requires a switch chip, but it can be done on a system level. So later on, Lattice will also offer a reference design and schematic on how you can do that. So, but for now, our evaluation board uses the Type B connector.
Yeah, PJ, as a matter of fact, we switched over to the USB-C. So all our reference designs use the USB-C.
All right, you're ahead of us. That's great. Okay, and I think the next one, okay, the next two, yeah, the next few are for you. they're curious about the mechanical specifications, weight, temperature, vibration, etc. How do you address that?
Yeah, that's really important. In fact, the design of the SOM was the physical design of the SOM is such that it can be used in a high vibration environment. The connectors are used in drones today, which is an extremely high, really nasty environment from a vibration point of view. So we know these connectors work. They've been used for multiple years by some of our partner companies. The SOM has physical retention, a notch in it for a screw so that you can actually screw it down and have positive retention. In terms of weight, it's about 3 grams, which is great for a drone. And connectors are really cheap. These are just widely available, I think, under $1 for these high density connectors. In terms of mechanicals, this is a 1x1 square, 1 inch by 1 inch square. So pretty compact design. And on the vibration side, we are going to be testing it for a typical drone operation, which I think is one of the more aggressive mechanical vibrations specs.
Okay. Well, I think, lots of great questions. We are really running out of time. So what we'll do is we do receive some of the questions and we'll get back to you offline. But thank you all for attending today's breakout session. I hope you enjoy the rest of the Lattice Developers Conference. Thank you very much.
Thank you so much.
Thank you, Venkat.